Is it on? Okay. Hi, Dr. V. So this is my extra credit video for exam 3. So I'm going to be doing the first question, and I'll read it off of my phone. I'm sorry that I'm not in front of a whiteboard. I'm doing this at the last minute, to be honest, but I am going to be using this, and I will be using a Sharpie, so it'll be clearer for you. I know the previous extra credit video that I did wasn't too clear, or it wasn't clear on paper, so here we go. All right, so number 1 says, a first order reaction is 24% complete in 19.7 minutes. How long will the reaction take to be 85.5% complete? Calculate the rate constant for the reaction. All right, so first what I'm going to do is, let's see, so the equation that we're going to be using is as follows. It's going to be A equals A0, E negative KRT, which is this, and we're pretty much going to be using this equation just because it involves the rate constant. It also involves like quantities, or the quantity of the what's it called? How can I explain this? The quantity of the material that's decaying at a first order reaction. So this is the original, and this is the after a certain period of time. So let's see. So now what's different with this question is that there are percentages instead of like actual amounts. So let's see. First we have 24% complete. So instead of saying, or instead of doing it as, we don't know what the 24% is of. We don't know if it's of 10 grams, 100 grams. So what we're going to do is just do 100 minus 24. Let's just assume we have like a 100 grams or something. So, or 100% of it. So we take 24 away, we will have 76% at 19.7 minutes. So that's what we have here. And then we can do the same thing for a reaction that will take, or to calculate the time that will be for the reaction that takes, wait, how long the reaction takes? For the reaction that will be 85.5% complete. So we will do 100 minus 85.5, and that will equal 14.5% at t equals question mark, because that is what we're trying to find right here. All right, so let's simplify this equation, because first we have to find the rate constant. We can't, this is the variable that we're looking for that's going to be the same between the 24% material and the material that's degraded at 24% and the other material that's degraded at after 85.5%. So we will do that by just manipulating that equation that I just showed you, this one right here. Alright, so we have A over A0 is going to equal E to the negative KRT. Excuse me, KR is a part of rate constant. That's the rate and rate, puts the rate and rate constant, or the R and rate constant. Anyway, so this is what we have here. Now we need to isolate, we're trying to isolate the KR. So what we're going to do is just take the ln. This will cancel out the E, and this will bring the KRT down from this, and we'll have the ln of this. So let's do that right now. Ln of A over A0 equals negative KRT, or excuse me, yeah, KRT, rate constant times time. But let's move this negative over. It'll make our lives somewhat easier. So KRT. Alrighty, so we have the time, or excuse me, so we have the quantities. Yes, we have the quantities. So it'll be negative ln of the percent that got, or the percent, hold on, how can I explain this? Because the percent, yes, the percent that got degraded, which will be 76%, because the 24 value just represents first order reaction that is 24% done, but 76% still remains. So we're going to put 76 in the numerator, and 100 in the denominator, since that's the total amount. And we know that that happens at 19.7. Oops, yes, it's perfect. 19.7 minutes. All right. So we have KR, and we're doing 19.7 minutes. All right. So we have KR. Now we just have to divide 19.7 by ln, negative ln of 76 over 100. And let's see what we get. Got the calculator. I don't think you can see it, so you'll just have to trust me on this. ln of 76 divided by 100, which is 0.76. And since it's going to be less than 1, it'll be negative. But we have that negative on that side, so it'll come out to be positive. And then we just divide it by the minutes. And we get KR. You can see it. Hopefully there's a glare. But KR is equal to 0.0139 minutes, but with the negative 1 of the exponent, because it's not going to, just because the time was in the denominator. So it's going to look like this. And I will start a new page. So we know the KR. Let's box that off. So we're clear on that. Here. Alrighty, so now let's move on to the final part of the problem, which is trying to find the time that it takes for 14.5% or 85.5% of the reaction to be complete. So what's remaining after, after 14.5%? Let me find a good page to do this on. In fact, sorry for the long noise, I'll rip this off. And we'll do it like that. Alright. So we have the KR. It's 0.0139, 1 over minutes. And we're trying to find how long it'll take for the reaction to be 85.5% complete. Alright, so we're going to use the same formula, which is A. If I don't get this ink on my desk. Anyways, A equals A0 E negative KRT. Our lovely initial equation. Our first equation. Alright. So we can set it up the exact same way we did with this, except we are going to be looking for time. Gosh, I get emails after emails. Anyway, so with that being said, we can, instead of just like writing it all out, we're pretty much, you know what, I didn't write it out. I'm sorry, this is such a mess. Alright, so we can do, so we'll take that, we'll divide A over AO, which will equal negative E, oh gosh, E negative KRT. It's been a long weekend, I'm sorry. And then we'll take the ln of it to cancel out the E value, or natural log should I say, and we'll get negative KRT. We can bring the negative over, negative ln A over A0, and that will equal KRT. And now we're trying to find time. Here it is so far. Now we're going to find time, so we just divide KR by this side, and we will, or by both sides technically, and we will be able to find T. Alright, so let's see, negative ln A over AO divided by KR, and that will equal T. So your equation so far should look like the following. Alright, I'm starting to get anyway. Bad joke. Alright, so let's plug in some some values. So we have negative ln. So we are looking for the so A, which is in the numerator, will be 14.5, since that's 14.5% that is remaining of the product that, or of the material that was reacted. And then we're going to divide it by 100, since that is the total amount. And we're going to divide this by the KR that we found, which was 0.0139 minutes with the -1 exponent. I'm sorry, I don't know the technical term of it. Per minute. Per minute. There you go. All right. And yeah, you just got to do the math for it. So let's do that. So we have ln of 14.5 divided by 100. And that comes out to be negative, but there's a negative on that side, so it actually comes out to be positive. And then you just divide it by 0.0139. Divided by 0.0139, not 193. And the minutes, hold on, let me show you. So the minutes unit, since it's so I have it written as this, but honestly it can technically be written as 1/minutes. Like this, and since it's in the denominator right here, and this is in the denominator, and how, you know, math works, the minute will actually come up to the numerator, and that will give us our final answer of 138.9 minutes. And that is our final answer. If you want it in hours, because I don't understand 138.9 minutes, you can just do a little, really messy, 138.9 minutes, multiply it by 1 hour over 60 minutes, a little good old dimensional analysis in the corner, hopefully it's not getting too messy, divided by 60. Yeah, and that is like going to be approximately 2.32 hours. So if you're in a rush like I am, that's probably not the best thing if you wanted to grade it, but I guess that's science and you'll have to deal with it. Alright, this is 12 minutes long. You're probably tired of listening to me talk. So yeah, have a good day. I hope you like this and that it was somewhat enjoyable, and yeah.